Hi, in chapters 5 and 6 we cover temperature concepts and controls as well as the Earth's temperature patterns. We've seen this diagram before. We can see this Earth-atmosphere energy balance. These are all the things that can happen to insulation if it gets reflected, absorbed, hits clouds, eventually makes it to the Earth, and some of these convective currents and energy transfer as it maybe gets re-radiated back into space. Insulation is absorbed by surfaces on the planet, re-radiated back towards space. Albedo, the actual complexion of the material, has something to do with that, and we talked about that before. Energy transfer takes place at individual atoms at an atomic scale. So we have conduction, we have convection, we have radiation. Energy by latitude, I think we've seen some form of this diagram before. We have incoming energy gain at the equator. At the poles, we have deficit, and it evens out. Okay, and we'll talk about some of the processes by which some of this energy where we have this gain or this surplus at the equator gets distributed towards the poles. We have diurnal, daily patterns between sunrise and sunset. Coolest temperatures occur after sunrise. Warmest temperatures occur, hours after noon. Not when we get the sun highest in the sky, because we have this absorbed insulation and this agglomeration or compounding effect. You can see a climate graph for Fargo, North Dakota, so we can see the temperature, and you can see the maximum input is in June, in theory, where the sun is highest in the sky, but the max temperature is in July because of this agglomerated effect here. And I thought this was kind of interesting here. You can see the precipitation, but you can see the temperature ranges here. In my previous classes, I had students go and interpret these, but we kind of moved away from this a little bit. But you can see this example and the relationship with the temperature range, the highest minus the lowest, versus the precipitation, all in the same graph. We have heat versus temperature. Heat is just a form of energy that flows from one substance to another. Temperature is the measure of the kinetic energy. And to be honest with you, temperature is measurable. This is what at the end of the day, this is what we care about. We have latent heat, we have conduction, convection, radiation. There are different temperature scales. We have Kelvin, which is, starts at absolute zero, but we're more familiar with Fahrenheit, and then, Celsius. In both 2017, 2018, I was in Europe, so, really warm days got up to 30, 32 degrees Celsius. That's about 86, 90 degrees Fahrenheit. You can see the different temperature scale. Celsius, the whole goal of Celsius was to have 0 as the freezing point of water, 100 to be the boiling point of water. So, and then you can see the relationship with Kelvin, which has an absolute 0, and then kind of Fahrenheit thrown in there that we're a little bit more familiar with. But you can see some of that, the average temperature is about 37 degrees Fahrenheit, 98.2 average temperature, but you can see some of these, the highs and lows, extremes that we've had around the world. Some of the temperature controls: latitude. Okay. Insulation, basically, the most important influence is latitude. You're never going to get really high insulation in Iceland or Greenland. You're just not. Okay, and then we throw into it factors like day length, solar angle, which are direct effects of latitude, and then other things that are more local, like altitude. Okay, so mountainous regions are cooler than sea levels. So we might have places like Denver, Colorado, which is generally going to be cooler than other places, say, Bismarck, North Dakota, because it's lower in elevation, even though they're at about the same latitude. I think Bismarck might be a little further north. So you can see this example right here with Concepcion versus La Paz, and this is in Bolivia. La Paz is at about 13,000 feet. I think it's one of the highest national capitals. Okay, but they are at about the same latitude, so they receive the same amount of insolation. But you can see the temperature ranges in Concepcion versus La Paz as a direct result of this elevation. Okay. Cloud cover, it's a moderating influence. We know it's still relatively warm out if it's cloudy. Okay. And then land water heating differences. I mentioned this in a previous lecture, but we have this maritime effect, meaning places near the shore are going to have much lower temperature ranges. I've been to Alaska, and believe it or not, in this part of Alaska, it doesn't get down to freezing that much even during the winter because we have this large body of water, Pacific Ocean, Gulf of Alaska, that aren't going to freeze up or warm up in the winter very much or cool down. Okay? Large bodies of water take a long time to heat up and cool down. Okay, you'll notice. So you go to the shore or go to the ocean. Even in May, it's still relatively cold, even though the air temperature is nice because it takes a lot of energy to heat up that water. With land, you're heating up maybe the upper 6 inches of it from insulation, but some of this insulation could penetrate down to 100, 200 feet into the ocean, and it's got to heat up all of that water compared to land. So you can see how this, what we call continentality versus these maritime. We've got a couple places here in Russia. You can see here how the temperature changes here. The temperature ranges are really distinct, where this more modifying influence here, basically looking at this red line, the difference between the high in the red and the low in the red is a lot different than the low in the red and the high in the red here, even though they're at about the same latitude here. And it's the effects of continentality versus this maritime influence. Specific heat and continental maritime effects, I've talked about this before. Insulation doesn't have to go too far into the land, but with insulation, it penetrates much further into the water and it has to heat it up more. We can see the Gulf Stream, so the mixture of warm water from the south, cooler water in the north. We have isotherms. I've had essays on isotherms in the past. So you can see some of these isotherms here, lines of the same temperature. And then temperature ranges, okay? Where we have high temperature ranges here, places further inland. Okay, this example here with Russia here. You can look up here in Canada, okay, high temperature ranges. Okay. And then you can see how some of these temperatures get really high, extend further and further north. And then you can see your global map, okay, from min to max. So you don't have a lot of temperature range here. Oceanic circulation, week number 5, or the next chapter here. We have barometers, and then air pressure. So essentially air pressure is the weight of the atmosphere at any particular location, and it's useful to weather forecasters to talk about weather trends in the near future. Okay, we have weather, we have climate. Climate's the study of weather over extended periods of time. Weather is the condition of the atmosphere at a given time and place. So we have the different measures of air pressure, the highs and the lows. Then we have winds. Basically, winds are the movement of air across short local distances. Typically, winds flow from areas of high pressure to areas of low pressure. Okay, and wind directions and names. Winds that come out of the northeast are called northeast winds. So they discuss the direction they come from as opposed to where they go. So where they come from. So this would be a north-northwest wind coming from Durham to Wilmington. We got global winds. They're not caused by the rotation of the earth. They arise from air pressure differentials, this high pressure, low pressure across space. And then this is what we call our pressure gradient, the movement of wind from high pressure to low pressure. Okay. So we have strong winds where this pressure gradient, the differences in temperature, is a lot more pronounced than low pressure, when it's much more spread out. So you can see the pressure gradient map for the continental U.S. And then we have the Coriolis effect, or the force, deflection or movement due to the Earth's rotation. So these winds aren't going to take a straight path, but are going to be affected by the rotation of the Earth. In the northern hemisphere, this deflection is to the right. Southern hemisphere, its deflection is to the left. So you can start to see how in the northern hemisphere they're going to be deflected towards the equator. Southern hemisphere directed towards the equator. And we can see this as a cross section. And you can see the pressure gradient force here. We have cyclones, anticyclones. Pressure gradient draws air straight from high to low. And you can just see the development of these new circulation patterns here, where we have cold fronts and warm fronts, movement of these air masses coming from different places, which we'll talk about in a bit. And then we can start to see the movement of air as affected by the rotation of the Earth and these pressure gradients. Okay. So you can start to see these cyclones and anticyclones here. So you can see in January, the average global barometric pressures, the subpolar highs, polar highs, subpolar low pressure cells, polar high pressure cells. So you can start to see these patterns and how we start to get the westerlies and subtropical highs and northeast trade winds. And so how in the United States we've got these trade winds coming down from the Tropic of Cancer or so down to the equator, but then they go back in the other direction. So this warmer water and air and temperature goes up to Europe. So even though the latitude of places like London is about 50 degrees, is about equitable to Edmonton, Canada here, they still have relatively warm weather. And then you can see a cross section of these wind cells here. And we have jet streams. And to me, the jet streams kind of separate these cold air masses coming down during the summer. These kind of peak down a little bit further. And then we have an area called doldrums where there are no or little winds, where these different latitudinal layers meet. And basically, weather happens when air masses collide with each other or with mountains, where we have some change. We have troughs, we've got ridges, we've got local winds, land, sea breezes, mountain valley breezes, just basically due to differential heating. You see palm trees in Dublin, so this example that I was talking about before. And while I'm here, I will kind of mention this. In the summer of 2018, I was in Cologne, Germany. So if I zoom out here, I'll X out here.
You are 0.16 miles, 0.26 kilometers, north of the center of No-Chill Park, North Carolina.
But if I zoom out here, you can see where these are relative. You can zoom into Cologne right here. This is in Google Earth. I can right mouse click. What's here? We're at about 50 degrees north latitude. 50 degrees north latitude. Fredericksburg, right about here. What about 38 degrees? So 50 degrees is going to be a little bit further north. This is 45. So when we're looking at Europe here, the latitudes are going to be what we experience in northern Canada. So like I was talking about before, we've got these westerlies that come from the west that bring this warm air and warm water and affect these areas up here. Okay, so those palm trees that you saw before were up in Ireland. You can see how far north Ireland is. So that's about it for this particular chapter.